Hello. It's me, Dia, the Sugar Lump Fella. Oh, this? It's another unique costume change. I chose pink plushy cheeks because I want to see how it fits my avatar's cute side. Anyways, this certain episode will be a special one. And no, I won't be shoving a parameter in your face and forcing you to sit there and watch me locate the pseudo-foci. Instead, throughout this video, I will be describing these parameters called Bézier curves, and then explaining how they are drawn and visualizing how evolutes work in general using the parametric curve. A Bézier curve, in layman terms, is a flexible, general curve whose shape is customizable by these movable pins called control points. Mathematically, a B-curve is a parametric curve of any degree. They can be linear, quadratic, cubic, quartic, etc. But the higher the degree, the more control points you'll need. And to provide intuition, a polynomial changes more directions the higher degree it is. So analogously, you will need more control points to change a B-curve's direction. Since the B-curve is a kind of parametric polynomial, the curve in its most general case is expressed as the sum from k to n chooses k, p of k, 1 minus t, power of n minus k, t to the power of k, where pk are the control points, n is the curve's degree, and k is the sequence of numbers from 0 to n. I will not go in depth of why this expression is written like the binomial theorem or why this generalizes all Bézier curves. Rather, I will only explain how these parameters work geometrically in the graph. To explain the B-curve structure, one must start with its simplest form, a line. The linear B-curve, or you could say the B-line, is created by two control points. Because connecting 2 points makes a line. But more precisely, imagine another point traversing across that line from and to the 2 points. The course of this moving point then serves as the locus that traces the linear Bézier curve. And that's basically it. Now what about a quadratic B-curve? It's quite the same thing, but with another layer of that same thing. Instead of 2, quadratic B-curves now require 3 control points to be drawn. Briefly, these points are first connected by 2 lines, one to each pair. Then these 2 lines serve as paths for 2 moving points to be drawn, traversing across each pair of points like a conveyor belt. After that, another layer of the same is emulated, where 1 line is drawn to connect the 2 moving points. This makes a line that is transformed accordingly by the endpoints. And like before, this line is traversed by another moving point on top, which must be synchronous to the first 2 points' motions. At last, the trajectory of this final moving point serves as the locus that draws the Bézier curve of the second degree. If you have the pattern in your head, then I'm sure you have an impression of how a cubic Bézier curve is generated, so I'll be brief. First, start with 4 control points. 4 control points are connected by 3 lines. Then 3 moving points travel across 3 lines. Then with the 3 dynamic points, 3 dynamic points are connected by 2 lines. 2 moving points travel across 2 lines. Then with the 2 dynamic points, the 2 dynamic points are connected by 1 line, 1 moving point travels across 1 line. And finally, the last moving point's combined root is the locus that traces the cubic B-curve. This layered process of line and point generation carries on to the higher degrees containing even more control points. And even more control points creates more complexity to its shape. On top of that, imagine manifesting this complexity of the B-curve by manipulating the curve's shape through the control points. This characteristic makes the Bézier a very flexible and versatile curve, and at the same time customizable. So I hope I gave you some insight about this curve's general behavior when we happen to get a hold of the Bézier curve. On a related note, if these Bézier curves are flexible, versatile, and all that, how can Bézier curves tell us more about evolutes? Bézier curves, as you have figured, can change as many directions as it wants. The changing of that direction presents a curvature of that curve. Since adjusting the control points controls the curve, one can also control the parameter's curvature and consequently the evolute by a simple drag of their mouse or finger if they're mobile. By interacting with the Bézier curve's shape and curvature, one can witness the consequent change experienced by its evolute. Speaking of interaction, there is a Desmos link under the description where you can adjust the curve as well as the evolute in front of the screen. There will be directions of what to do in the Desmos activity, so don't worry too much on figuring things out. So enjoy playing Mathematical God yourself. All the while, let's briefly explore the varying behaviors of an evolute through the manipulation of this curve. To start, a common behavior of the evolute is a single cusp drawn under a curve, where at some point the parameter gets very curved, making the evolute create this peak. Another behavior of the evolute is a triple cusp, a deltoid I call it. This happens to seemingly flatter curves, where there exists 3 pseudo-foci in the evolute, causing it to peak thrice. The next behavior of the evolute is a quadruple cusp, an asteroid I call it. This kind of behavior can happen if the curve is smooth and enclosed, where the last control point meets the first. And to derail for a bit, the 4-peak behavior in the closed curve relates to this thing called the Four-Vertex theorem. Roughly speaking, the theorem describes the existence of no less than 4 evolute cusps in a smooth closed curve, never 3 or 2. I want to bring this up because it says a lot about curves and probably the universe, so the theorem link is under the description. But going back to evolute behaviors, since we have 1, 3, and 4 pseudo-foci, how about 2? Well, that case requires some precision because attempting it requires one to imitate or trace a quartic x⁴ function to your control points. If the result curve is not precise enough, there will be a third cusp that is way up or way down relative to the curve's direction, or also some other third consequence I may not know yet. But those are 4 of the evolute's behaviors based on manipulating a Bézier curve. I think there are some other cases like 5 or 6 in one curve, but maybe you can find that out yourself and let me know. That'll be all for this video. I hope you enjoyed having a sense of divinity by puppeting some weird funny doodles on the screen, and at the same time, mark a fundamental experience on curves. Again, Desmos link is in the description. Check it out, and try to create 4 of the evolute cases, and have some overall fun with the B-curves. That's about all I can present in this short video. So thank you so much for watching, and see you next video.